Welcome to this video lecture on the topic applications of Maxwell's equation. So in the previous lecture we have seen the different uh, types of Maxwell's equation derived from basic fundamental laws of electromagnetism. So there are four set of Maxwell's equation from Gauss law and Faraday's law, Ampere circuital law. So these are the four Maxwell's equation derived. So we can apply this Maxwell's equation to solve the electromagnetic field problems. So let us see the example problems. So to solve an electric field. So consider the electric field propagating in the free space as the E value is given as Em sin omega t minus beta z ay cap. So from this we have to find D, that is electric flux density, B is magnetic flux density, and H vector is magnetic field intensity. So first of all, let's take the relation between electric field intensity and flux density. So it is D vector equal to epsilon into E. So we know that epsilon is the permittivity of the medium. Here the medium is free space. So epsilon is written as epsilon naught. So D equal to epsilon naught into E vector. So in the problem, E vector is given. So we take the E vector and find D is equal to epsilon naught into E. So according to Maxwell's equation, we know that we are taking the second Maxwell equation that is derived from Faraday's law. So del cross E equal to minus dou B by dou T. So from this we have to calculate curl of E vectors. It means del cross E. So we are applying curl formula in determinant form. So it is equivalent to minus dou B by dou T. So solving the matrix, and it is equal to minus dou B by dou T. So from the matrix we get beta Em cos omega t minus beta Z into Ax cap. So integrating this equation we get B vector is equal to minus beta Em divided by omega sin of omega t minus beta Z into Ax cap. So using the Maxwell's equation, first of all we have found B vector, that is magnetic flux density. So next we are going to find magnetic field intensity. So because we know the relation between B and H, so B equal to mu into H. For free space, mu can be written as mu naught. So B equal to mu naught into H. So from this relation we can rewrite H vector as B by mu naught. So substitute B vector value in this. So H can be written as minus beta Em divided by mu naught omega sin of omega t minus beta Z Ax cap. So from this magnitude term is written as Hm. So we get the magnetic field intensity value. So like this we are using the Maxwell's equation of Faraday's law. We have found B vector and H vector. So in the problem electric field value is given. From this we have found out the magnetic flux density and magnetic field intensity. Let's take another problem. Here the electric field vector in free space is given. E vector is Em sin alpha cos of omega t minus beta Z into Ay cap volt per meter. So we can apply the same method as previous one to find the H vector, that is magnetic field intensity. So we consider Maxwell's equation del cross E equal to minus dou B by dou T. So we are going to find del cross E. It is the curl of E vector in the matrix form. So from this we have found Ey value. So let's take Ex is 0, Ey is given, and Ez is 0. So from this we can find the matrix determinant, and it is equivalent to minus dou B by dou T. So the answer is minus beta Em sin alpha sin of omega t minus beta Z Ax cap. So from integrating this we get minus beta Em sin alpha. Again the another integral is sin of omega t minus beta Z dt Ax cap. So after integrating we get B vector as beta Em sin alpha 1 by omega cos of omega t minus beta Z Ax cap. So this is the magnetic flux density value. So from this we can find the H vector value using the relation of B by mu naught. So substituting the B vector value, we get H as Hm sin alpha cos of omega t minus beta is at Ax cap. So in both the problems we have used the Maxwell's equation of Faraday's law, and we can find the magnetic field intensity and magnetic flux density. So similarly we can use other Maxwell's equation to find the magnetic field and electric field values. So summary of Maxwell's equation. So first one is derived from the Ampere circular law. In the point form, it is denoted as del cross H equal to J vector plus dou D by dou T. It means the curl of magnetic field intensity, it gives the current density plus dou by dou T of D. It is the uh, change in electric field. So either the conduction current or displacement current gives the magnetic field. And second equation, del cross E equal to minus dou B by dou T. So it is derived from Faraday's law. It is change in magnetic field produces then electromotive force. And third one, del dot D equal to rho V. It is Gauss law for electric field. It is the divergence of flux density or total flux is equal to total charge enclosed by the surface. So it is taken as rho V, volume charge density. And fourth one, del dot B equal to 0 or integral B dot ds equal to 0. It is Gauss law for magnetostatics or law of conservation of magnetostatics. So these are the references. Thank you for listening.